Greetings to you. We are coming nearer the closure of the course, and now we are going to discuss only the detectors followed by applications. Yesterday we were discussing about the detectors, and I had talked to you about the thermocouple detector. Thermocouple detectors are basically very useful in most of the detectors where the temperature difference can be measured up to 0.01 degree centigrade or Kelvin. We can measure that, and they are very useful. So, yesterday I had shown you this slide regarding this thermocouple detector. I am not going into details because yesterday I have already covered it. Okay. So, but I had also covered that about a little bit about the thermocouple characteristics. I had shown you these 6 thermocouples. One is indium, antimony, etc. And this is second is lead, tin and tellurium, lead, tin and tellurium at different temperature, pyroelectric, thermistor and thermopile, etc. And you have to maintain them around room temperature, these 3, that is pyroelectric, thermistors and thermocouple, approximately 300 Kelvin, but the others you need a coolant because they work at very low temperature. So, they become costlier, and the maximum number of IR nowadays what you see all have thermocouples as the detectors. Okay. But there are other detectors also. For example, this I had shown you thermistor functions, but it functions by changing the resistance when illuminated with IR. Okay. These are all made of sintered oxides of manganese and things like that. And I was about to teach you about the pneumatic detector yesterday. So, this uses the pneumatic expansion of a gas as a measuring device. Okay. So, the unit actually consists of a small metallic cylinder on which I put a expandable frame, diaphragm. So, first I take a cylinder, put some gas in that, and then put a seal of a gasket which is expandable. So, the it is closed. Normally we do not need any other radiation to fall on that. So, the gasket is closed by a rigid blackened metal plate. We need a metal plate to keep it stable, and that is about 2 mm square, okay, at one end, and a flexible silver diaphragm at the other end. It is a very simple this thing. I will show you very shortly what is the structure of the how it is made. So, the chamber, now we have a metallic cylinder with a frame, and we have to fill that. We fill it with argon, xenon, either of them. We fill it with xenon, and the radiation falls on the blackened plate. Okay. When the blackened plate is there, it will absorb all the radiation that is falling on the black plate. So, it gets heated. So, the heating causes the gas to expand. So, but where it will expand? It has to expand. One side is the metal plate, top side is the flexible diaphragm. So, it will expand and push the diaphragm upwards. Okay. So, what I do is when the diaphragm is pushed upwards, it stops a radiation fixed above a particular level. That means radiation will be cut off when it expands. Okay. It is just like entering a lift. When you are entering a lift, until you reach the lift, it does not show you anything. It may be closing or whatever it is, but the moment you put your leg, lift will sense that somebody is coming in and it will open again. So, that is how this diaphragm and the IR radiation are positioned. So, the moment the diaphragm expands, IR radiation gets cut off. Okay. So, this obstructs the light path falling on a phototube. Once it obstructs, it will not reach the detector placed across the cylinder. So, this distortion alters the plate separation and therefore, the capacity. So, the radiation, so long as the IR radiation is cut off, the absorbance will come down depending upon how much it is cut off. Okay. For 10%, 20%, 30%, it is percent transmission anyway, and the capacity would be 100%, that also can be programmed, and the response time of this detector is 20 milliseconds. Okay. So, 20 milliseconds, that is quite similar to TC. So, if it is quite similar to TC, we can use Golay pneumatic detector as well as thermal conductivity detector, both. So, it is best among the lot, because once the Golay detector pneumatic detector is in place, it has got a long life. Okay. And the cost is also not very much, that is production cost. Okay. So, this is how the Golay pneumatic infrared detector looks like. Here what I have, look at this slide carefully. I have the radiation coming here, infrared radiation, all parallelized, and then I have a lens here to focus and fall on the black and metallic plate. This is the metallic plate. Okay. Pneumatic chamber is here, metallic plate is outside here. Okay. The edge. Okay. And the whole thing is put in a heat sink. The shaded portion in this figure is the heat sink. That means, as soon as the heat is detected and it is off, it needs to be dissipated for the and made ready for the next wavelength to come in. That is why we need a heat sink in most of the thermocouple detectors. Okay. Or even Golay detector. This is also based on the heat detection only. So, here this is the infrared transmitting window made of KBr, sodium chloride and things like that. We have already discussed about it. And this is an absorbing film, IR absorption film, and there is another flexible mirror here, and then I have the line grid image coming here, and this is the actual line grid, and this is the diaphragm. Okay. This is the line grid. That means IR radiation can vary only between this and this maximum. This is 100% transmission on the top. Here this is a double beam type like thing. So, it goes here and goes here, visible light source is there, and 100% and absorption maximum. So, line grid image is obtained, and then I have another small mirror here, and then it is taken through this, and then I have a photoemissive cell, because the radiation source IR radiation must finally fall on the photoemissive cell to generate the electricity current. So, that current is measured always. See, what in general, whatever we are going to measure is the heat difference, and that heat difference is connected to thermocouple or whatever it is, the heat difference, and the IR radiation also should be falling on a photoemissive tube, photoemissive cell, which will generate the current. So, finally what is recorded is a current only, but the mechanism of IR detection is different. That is why we have different detectors. And so Golay cell is one of them. Now you can we can go back and you will understand this slide much better, because it is a Golay pneumatic detector. It uses the expansion of the gas, that is xenon or argon. The unit consists of small metallic cylinder closed by a rigid blackened plate, etc., etc. So the gas, when it expands, obviously it will obstruct the IR radiation reaching the detector. Okay. So that is how the detector works. Then we have other types of detectors. They are known as photon detector directly. The photons incident on a semiconductor. These are all very common nowadays, and so the photons will produce the electrons and holes depending upon whether it is NP type or PN type. If it is NP type, it will produce electrons first. On the other side, P side, it will produce holes. So that is the internal photo effect. A sufficiently energetic photon raises an electron to conduction band. That is just like what we have already discussed. That is, most of the metals have a conduction band and a Fermi band, and so the electrons are raised, and then the detection can be carried out. So in a photoconducting detector, the presence of electrons in the conduction band will lower the chip's resistance. That is the idea. So the intrinsic electron hole pair, both of you can't produce an electron without producing a hole. So they are all there in as and when they are produced. Every electron will produce a hole, electron removed for current generation or current detection or whatever it is. It produces a hole in that. The hole also can move. So the electron is raised to the conduction band of the semiconductor. So extrinsic excitation refers to the electrons raised from or to the impurity doping levels. Normally most of these NP type detectors are made by doping the silicon or germanium with different metals. That is a different science by itself. But it is already taught around degree level physics classes. So you can look it up, and the doping levels depend upon the intensity what you need. So you can dope it with 1%, 2% or 10 ppm depending upon whatever is the required application. So within the forbidden band of the semiconductor only we have to dope. That is the limit which is set by the doping element. So a bias current or a voltage registers this change as the output. That is all. So photon detectors are also popular nowadays, and when you buy an instrument, IR instrument, you should find out which are the detectors employed in the infrared spectrum. So the cost, quite often the cost is also dependent upon what type of detectors they are used. You can also calculate the losses, etc., lifetime and all those things, and decide on a proper IR instrument with a suitable detector. That is why we are learning all these things. So photovoltaic detectors generate a small voltage in the INSB, that is indium antimony PN type junction in single crystals. Now you should remember the figure what I had shown you earlier. That is, should I show you once again? Okay, let me, just to remind you which figure you should go back. This is the figure. Okay. So go back to this figure and you can correlate what I am going to teach you now with these things. So photovoltaic detectors generate a small voltage in indium antimony PN type junction in single crystals. So the P type is laid as a thin layer over the N type. So both of them are sandwiched. The band gap is approximately 0.23 electron volts at liquid nitrogen temperature, because you remember they were all around 77 degree Kelvin. So, lead tin telluride or detectors are also there. They extend the spectral sensitivity to larger wavelengths, that is 5 to 13 micrometers. So, if you want to do far IR, then you need to go for lead tin telluride detectors, because up to 10 microns, millimicrons now is far IR. So, that is why you should remember the range of infrared, near infrared and then infrared and far infrared. So, the lead tin telluride can be used from 5 to 13 micrometers. So, most of those things are used for infrared work for coordinate complexes of the metals. Okay. So, the other range is 6.6 to 18 micrometers. When we use it with a current mode amplifier, response time, another important factor for you to learn about the response time of all detectors when you buy an instrument. So, response time is of the order of about 20 nanoseconds. That is fantastic, isn't it? So, there are different ways of doing it. Now, I come to the applications of infrared. We have finished our discussion with infrared instrumentation. Why I want to spend some time on applications is I want to reassure you about the complexity of the infrared. Don't be afraid. Why? Because the moment one sees an infrared spectrum, what you will see actually is nothing but a few peaks on a graph paper, and the number of peaks you will see. So, one's first reaction is a bafflement. What do I do with so many peaks? How do I identify? And what is the thing I am looking for? Like that, the questions will be arising in your mind. So, in general, what I want to tell you is the IR peaks appear for the same functional groups in the same area. So, if you are looking for a particular functional group, that is characterization of a compound in terms of its functional group. When I give you a sample, whether it is an aldehyde or amine or something like that, you do not have to go to table or working table for chemical analysis. You just take the IR spectrum, and if it is an amine, it will show amine functional group. If it is aldehyde, it will show aldehyde functional group. Carbohydrate, that will show, and then carboxylic acid, that also will show. Like that, different functional groups will show peaks exactly at the same position. So, without knowing the actual compound, you can straight away classify the organic compound, unknown organic compound, that it is an amine, it is an aldehyde, it is a ketone. Like that, one can classify. So, the steric effects and electrical effects, etc., they are always there for different compounds having the same functional group, that is propanaldehyde, butanaldehyde. There will be some differences, okay, but both of them are aldehydes. So, they have to show aldehyde peaks at the exact spot where aldehyde peak is expected. Other peaks one can identify whether it is propanaldehyde or butanaldehyde by looking at the propanaldehyde IR spectrum, okay, or butanaldehyde IR spectrum, you can decide. Like that, any compound you want to identify, you take the spectrum of a well known purified compound and see how is the pattern. Okay. So, now take a look at, I am going to explain to you what are the different kinds of functional groups that we come across, where to expect the peaks. Look at this slide now. I have written here the carbonyl group. This is C double bond O. Carbonyl group occurs in aldehydes, ketones, carboesters, and then carboxylic acids, etc. So, CO stretching frequency vibration is the same for acetone or di-N-hexyl ketone or any ketone for that matter. Here I have written only the di-N-hexyl ketone, but it can be same. So, it is different from a carbonyl group, that is CO group of acetic acid. Why? Ketone and acetone is acetone is a ketone and hexyl ketone is a ketone, but acetic acid is having a part of the functional group. CO is common, remaining is OH. COOH, if you remember a little bit of chemistry, the actual functional group is COOH. So, all these aldehydes, ketones, etc., they all share common CO bond plus another functional group. Aldehyde will have H as the another part, and ketones will have another functional group. Acetic acid will have OH group, like that, different oxygen. So, I have the IR spectrum will be different for acetone, dihexyl ketone, but it is different from acetic acid, and also it is different from cyclobutane. Now, when I say cyclobutane, you should compare acetones, hexyl ketone, di-N-hexyl ketone and cyclobutane. So, none of these would be similar IR spectrum, that is acetone, di-N-hexyl, cyclobutane, because of the steric effects. So, this is what I was trying to tell you. The functional group will appear, but actual spectrum will be entirely different. Now, IR spectrum cannot distinguish a pure sample from an impure sample, that you must understand very clearly. A crude product, if you are carrying out a particular reaction, a crude product will have impurity also. So, the impurity is there, pure product is there, reactants are there. Okay. I want you to understand, whenever we carry out a reaction, we take a particular organic compound, we add some reagents, let the reaction continue, and then at the end of the reaction we expect a product. Okay. Either we heat it, add some chemical compound and then cool it and then distill it, whatever it is, whatever is the process. There are reactants, then there are products, then there are byproducts, then there are parallel products, intermediates, like that. If you take out a reaction mixture, you will have all these compounds, and infrared spectrum cannot distinguish any of these compounds separately. That is, if you take a reaction mixture, if all the compounds are there, it will show the peaks of all the compounds. It will be much more complex than any pure compound. So, one is clearly baffled by the complexity of the spectrum when you are following a particular chemical reaction. So, if I have a pure sample and some impurity is mixed in that, it cannot show that the sample is pure or impure. It will just show the functional group and keep quiet. It is up to you to decide that. So, how do you decide? You take a pure compound spectrum and see whether there is any change in the pattern of the pure compound IR and the current sample IR sample what you have taken. So, a crude product will show infrared peaks of all the reactants and the side products. Even higher molecular weight chemicals generally give very poor spectra. This you should understand. Okay. Now, look at this slide down. The progress, so what is the use of an IR, you may ask. So, if I am carrying out a reaction, the progress of a chemical reaction can be followed by drawing an aliquot of the reaction mixture and checking the infrared spectra for a specific functional group. That specific functional group should be part of the product or part of the reactant. If it is a reactant, the specific functional group peak, IR peak, will disappear, and if it is a product having a specific functional group you are looking for, then it will start appearing. Okay. So, if it is a reaction mixture, okay, the reactant is disappearing and product is appearing. Any time you take a mixture, both of them will appear. So, how will you follow a chemical reaction? You keep on looking at the both the peaks, okay, of the reactant as well as product specific peaks, and when the peak of a reactant completely disappears, you say that okay, the reactant is no more there, all of it has reacted. So, the product becomes pure. So, like that one can follow a chemical reaction using infrared. Now, look at this reaction. I have given you one example. What is this compound? This is R1 R2 CHOH. So, on the left hand side I have a reactant which is having a functional group OH, that is it is an alcohol, it is a secondary alcohol. So, when this alcohol is oxidized, this OH group will disappear and then I get a compound like R1CO R2, that is a ketone. Okay. If R1 is hydrogen, then I get an aldehyde. If it is not a hydrogen, then it is a ketone. So, the OH frequency of the reactant appears at 3570 centimeters inverse. This I had explained to you earlier also when I was introducing you to infrared spectrometry. Okay. So, OH stretching frequency this is, and this stretching frequency decreases as the reaction goes on, and this concentration of the secondary alcohol decreases, and it vanishes totally when all of it is converted to the product. Now, how does the product look like? Product will have a functional group known as ketonic group or carbonyl group that appears at 1725 centimeters inverse. So, when you are carrying out this reaction, you will be looking at the disappearance of the 3570 centimeters inverse and appearance of 1725 centimeter inverse peak in the infrared. This is how the application of IR becomes very common. So, the most powerful function of infrared is in establishing the identity of a sample by comparison using the same medium, because again the medium assumes a very important role in comparisons. If I change the solvent, IR may appear differently. So, the region 1430 to 910 centimeters inverse, this is where stretching of frequencies of carbon carbon, carbon oxygen, carbon nitrogen occur, and some bending vibrations also occur. So, you will assume you will know that almost all organic compounds will be having carbon carbon single bonds, many of them, and carbon oxygen bonds will be having single bond COH. Okay. OH is COH. So, CO single bond frequency will be there, and then CN single bond frequency. So, many stretching frequencies and bending frequencies occur between 1430 to 910 centimeters inverse. This region is known as fingerprint region. That means, you take a look at the pure compound, you will be able to immediately identify, oh, this compound is this spectrum belongs to a compound like this, and it is a ketone, it is this thing like that. So, fingerprint, you will also be able to tell whether there is oxygen or not in the compound, whether there is nitrogen or not in the compound, you can tell, because if the these elements are not there, the peaks corresponding to CO and CN will not appear. So, whatever you look, the real expertise of an infrared comes from looking at 1430 to 910 centimeters inverse range. Okay. This is known as fingerprint region. So, even if similar compounds show similar spectra, discernible differences do occur only in the fingerprint region. Okay. Take a look at this slide, very interesting. So, I want you to record this and give special attention to this. Okay. Now, several compilations are available already. The how do you compare? There will be I say you compare, but how do you compare? There are several compilations available in the textbooks, in the database, in the computer, probably microprocessor also. In the same computer what you are going to buy, there will be a database for different IR spectrum stored. So, when you are carrying out a particular reaction, all you got to do is simply recall the particular IR spectrum and compare, and the comparison also can be done using computer. That becomes much more easier than personal visualization of each peak. So, that is a little cumbersome. So, several compilations are available listing characteristic groups which can be used to characterize an unknown material. Take a look at this slide now. This compound, thus if a compound shows a peak at 1718 centimeters inverse, we can definitely say it contains a CO group, carbonyl group, but it could be an aldehyde, it could be a ketone, it could be an amide, it could be an ester, or it could be an acid. Further analysis of IR spectra by IR only or some other classical techniques are required to identify the compound. But if the IR spectrum does not contain these peaks, that is say 1850 to 1587, in that range, if the IR spectrum does not contain any peak or 1718 centimeters inverse, that is CO bond, so carbonyl group. If it does not contain, you can happily conclude that it has no CO group. No, so it is not a ketone, it is not an aldehyde, it is not an ester, it is not an amide, it is not an acid. So, elimination becomes very easy. Okay. So, this is another way of putting the infrared spectrum information to use. So, given below, I give number of examples here. These are easily interpreted absorption bands of some common organic compounds. I can't give you all. There are quite a few organic compounds with specific functional groups. It is not possible for us to cover everything, but it is not necessary also. What is important is to account for peaks that are not of the analyte. Okay. For example, if I am using a solvent, I have to discount the solvent peaks. If I am using a Nuzol, I had told you that it shows a doublet around 1400, 1398 or something, you have to discount that. So, like that the IR spectrum, in the IR spectrum several peaks need to be discounted corresponding to solvent, corresponding to the media, corresponding to impurity, like that. There will be a lot of variations, but as you continue your work in organic chemistry or infrared spectrometry, you will become an expert slowly. So, I am going to cover here only typical peaks, okay, typical functional groups and their this IR positions, so that you can remember a few, but there is no need for you to remember. Nowadays databases are quite efficient to remind you, and the IR peak what you get, they are also identified by the wave centimeter wave number, that is like 1458 centimeter. If you look at an IR spectrum from FTIR, you will not even see a graph, you will just see the peaks, but at the bottom of each peak the exact wavelength or centimeters inverse is printed. So, you do not even have to look where is the peak, what is the actual position of the peak, etc. So, Nujol shows CH stretching frequencies around 2950 and 28 centimeter 20. It shows a CH2 bending 1458, CCH3 bending at these things, and CH2 stretching frequency at 722 centimeters inverse. So, these peaks need to be discounted while you are taking the spectra in Nujol. Okay. So, look at the reaction now, couple of reactions I am showing you here. This is again a secondary alcohol CH3, CH210, CH2OH. Here I can expect OH stretching frequency for the reactant at 3448 and carbon oxygen stretching frequency at 1053, and here only the ketone I get one CO group, that is at 1758, and 1110 is the CO stretching frequency, okay, single bond. So, quite often you will also see that when you look at the IR peaks, you will see that sometimes we write into bracket S, into bracket W, into bracket M, like that. So, those notations correspond to strong, weak and medium. Okay. So, I do not know, look let us take a second look at the second slide. Okay. In the this is again a secondary alcohol, this is C6H6 group. So, it is C6 H2 H2 the 1 2 3 4 5 C6H10 OH. Okay. Yeah, C6H10OH, that is cyclohexanol, and it is taken in carbon tetrachloride solvent. It should show OH stretching at 3788, that we expect now, is not it, because it has got an OH. If I know the structure, I can expect where is the peak, and OH stretching frequency also I should expect. So, in dilute carbon tetrachloride, 3788 centimeter peak is more prominent compared to 3571 centimeters inverse. What does it mean? If I change the cyclohexanol or add a little bit of carbon tetrachloride, this peak is more prominent corresponding to CCl4 than 3571 peak. So, one has to be careful regarding how to take the spectrum. Okay. Similarly, if I have a ketone, I can expect a peak somewhere here, as cyclohexanones in the same range approximately 1715, cyclopentanone 1745, and pentanone alone, normal pentanone will show you 1715. So, anywhere a peak between 1715 to 1754 is the peak for CO group. We will continue our discussion in the next class. Okay. So, try to mull what I have been teaching you regarding the application. So, there is no need to get panicky, but a cool headed thinking will help. So, it will also, as you grow in experience, you will be able to identify many peaks yourself. Thank you. We will continue our discussion.